Okay, all set? Great. So our second talk this morning is from Sebastian Gomez from Space Telescope. I will wave at you when you have a couple of minutes to go. All right, take it away.
Sounds good. Thanks, Graham. Thanks, Gotham and all the organizers. It's nice to be back in an in-person conference. I am Sebastian Gomez. I am a postdoc at Space Telescope, also a member of the Transient Science at Space Telescope group. That's our little logo. And today I'm going to be talking to you about optimizing the search for exotic transients applied to LSST, where to me exotic transients means, in this case, superluminous supernovae and tidal disruption events. I'm going to tell you about how we have been using machine learning methods to try to optimize the search for superluminous supernovae and how that went. Current efforts that we have to apply these same techniques to find tidal disruption events, and then future plans to use this for LSST. So a quick background on superluminous supernovae. And what are they? Like their name suggests, they are very luminous supernovae. They can be about 100 times brighter than normal core collapse supernovae. They used to be classified based on a threshold, a brightness threshold, meaning anything brighter than minus 21st magnitude would be okay, that's a superluminous supernova. But then we started finding them at lower thresholds. We realized, okay, setting a threshold is not the best way to classify these things. So now they're classified based on their spectra. They are hydrogen-free, look like core collapse supernovae, they're blue, etc. But one of the big questions about them is what makes them so bright. So a normal supernova is powered by the radioactive decay of nickel-56. At most, a solar mass of nickel you'll see in a normal run-of-the-mill core collapse supernova. So it's normal to think, okay, maybe superluminous supernovae are just the same, but with more nickel. Turns out that is not the case. It does not work because the amount of nickel you would need to power that kind of supernova is like almost 30 solar masses of nickel, which is completely inconsistent with late-time observations. So it looks like superluminous supernovae are exotic in a different way. They are a different beast powered by something else. It seems that a magnetar-central engine is the most reasonable way to explain them. A magnetar-central engine is just a very fastly spinning neutron star at the center of the ejecta. And as it starts to slow down, it deposits this energy into ejecta, powering the super bright optical transient that we see. This model also manages to reproduce the spectra and the late-time flattening or late-time light curves that we observe in superluminous supernovae. But today's talk is more about how do we find them? What are the actual techniques that we use to find exotic transients such as superluminous supernovae? Right now, we are using all-sky unbiased surveys. In 2013, when Pan-STARRS started, it was discovering around 100 transients per month. Today, we are in the era of ZTF that's discovering around 1,000 transients per month. And I don't need to tell you guys that LSST is coming soon in 2023, 4-ish, and it's going to be discovering around 100,000 transients per month. But the problem here is that regardless of the number of transients you're detecting every month, the fraction of superluminous supernovae is the same because nature is not changing, right? So if you have a survey that is uniform, superluminous supernovae make around 1.5% in this random selection method, right? So if we really want to study them, we need efficient methods to optimize our purity, or like the efficiency of our telescope time, to catch as most superluminous supernovae as possible. And that is where FLEET comes in. FLEET is a finding luminous and exotic extragalactic transients algorithm that we developed to optimize the search for superluminous supernovae. So the way it works is you can take any transient from the transient name server. It will look at its properties, both the host galaxy properties of that transient and the light curve properties of that transient, and then assign it a probability of it being a superluminous supernova or not. And I will mention, related to the previous talk from Emily, that one of the points of FLEET is to do feature extraction really quickly. So it's using very simple models. So this can be run in like 6 to 12 seconds per transient on a regular laptop. And just a little context on what is a random forest classifier, which is what FLEET uses to classify these transients. A random forest classifier is a decision tree. You give it a transient with some parameters, some properties, and it's going to ask what are the set of questions that best separate these objects into clean or distinct classes. And it's called a forest because it uses many decision trees. So you just have like a group of transients and you fit them and run them through the decision tree. You want them to cluster into specific clean classes. So then when you get a new transient, you can run it through the same tree, ask those same questions and say, okay, property X is less than 5, property Y is less than 2. That means it's likely class number 2. For Fleet, we trained it on around 5,000 classified transients from the TNS, which includes around 187 superluminous supernovae. And we found that the most important features to distinguish superluminous supernovae from other transients are the width of the light curve. They are very slow. The time to peak, their color, and the normalized host separation, which is just the separation between the supernova and host galaxy divided by the size of the host galaxy. And another key feature here is that no redshift needed, because superluminous supernovae happen in very dim, low luminosity host galaxies, for which we usually do not have a redshift. So you can just feed it in a light curve, a catalog of galaxies, and it will tell you how likely it is to be a superluminous supernova without the need to know the redshift a priori. And how does it perform? This is what our predictions were 2 years ago when we started running Fleet. We said, okay, we expect a maximum purity of around 80% if we only were to observe things that have a likelihood of being a superluminous supernova greater than 80%. This comes at the expense of completeness, meaning we are losing out on a lot of objects, meaning completeness is only around 20%. But that is fine, given that we're observing like 1,500 transients a month from CTF and other surveys, which translates, given the expected rate of superluminous supernovae, this completeness and this purity, around 4 superluminous supernovae we could find a month, which is around 50 times better than just the 1.5% random selection. These were our predictions from 2 years ago. How did we actually do? Well, I'm happy to report it's working. Out of the 38 superluminous supernovae found worldwide since 2019, Fleet found 21 of them, so more than half of them. 20 of them were classified only by Fleet. 1 of them was classified by Fleet and by the REFIT team. But if we only look at the superluminous supernovae with a probability greater than 50%, we can see that the purity that we actually got in our observations is around 80%, higher than what we predicted. And the completeness, you can see this as an upper limit because this completeness is the number of superluminous supernovae found by Fleet divided by the number of superluminous supernovae found by everyone, because we obviously can't know which superluminous supernova we did not discover. So this is an upper limit, but still higher than when we predicted. So I hope I convinced you that Fleet works, that the algorithm is helping us to discover superluminous supernovae more efficiently, and that this can be applied to other types of transients, which is where tidal disruption events come in. So we decided, okay, this is another class of transients that is even more rare than superluminous supernovae, that we can use the same methods to find more of them. TDEs are what happens when a star comes into a supermassive black hole at the center of a galaxy. And as it gets close to the black hole, the star gets ripped apart, half of the star gets flung away, the other half gets circularized into an accretion disk, producing this bright optical transient that we see. And a lot of questions are open about TDEs. There's only around 40-ish, 60 TDEs that are well characterized in the literature, and they all show a wide array of features. Some of them have Balmer lines, some of them bound lines, some of them have radio and X-ray, some of them don't. So we don't have a cohesive picture of TDEs, which is why it's very important that we try and find more of these. And it's even harder than for superluminous supernovae, because TDEs make about 0.5% of all transients in an unbiased time domain survey, as opposed to superluminous supernovae 1.5%. So we again ran Fleet through it, trained the algorithm, and we find that to find TDEs, some of the most important features are that they're nuclear. Well, that's to be expected since they happen in the center of galaxies, and they're blue. Other important features are things like the light curve duration, the color of the host galaxy, and the time it takes for them to rise. In this case, we are a little more limited in the number of objects we can use. There's only 46 TDEs with decent enough light curves that we could use to train Fleet. But I can report on the predictions that we have on how we expect it to perform. And here I'm showing the same completeness and purity curves for Fleet TDE. And we see that we're expecting to find around a 50% purity for the same threshold of 80% probability of it being a TDE, which also corresponds to around a 20% completeness. What this translates to in the real world is that we could expect to find 1 to 2 TDEs per month, which is 100 times better than random selection, and it is about 20 to 50 times better than just imposing simple selection cuts, meaning I'm only going to observe things that is this close into a galaxy. This is still better than just doing those simple cuts. And now bringing it into LSST, we want to use these types of tools into LSST. So how would this perform there? So what we did is we took the light curves of not the light curves, the 30,000 realizations of the models of TDE light curves. So this is models of real data fed into the LSST 10-year baseline simulation using OpSim. So we have this LSST simulation that is just has all the pointings and depths and filters, and we just say, okay, what if we just put a bunch of TDEs in there, randomly distributed in time, space, and coordinates? How many can we recover, right? So we find here in the plot on the left, in gray, I show all of the injected TDEs, all of those 30,000. And in green is the ones that were detected just with one data point, just in the survey. And we see that most TDEs will probably found between a redshift of 0.5 to 1, and around 70% of the closest TDEs will be able to recover. But one data point is obviously not going to be very useful. So over here, I'm showing the actual net number of TDEs we're expecting to find. The black line shows 4 data points, which is the minimum that Fleet needs to work, and then 20 data points spread over 70 days, which is what we're calling a well-observed TDE. And in this case, for a rate of 10 to the minus 6 TDEs per megaparsec cube per year, which is roughly what the agreed upon rate is right now, that's around 10,000 TDEs per year that are going to be in the survey, well observed. That does not necessarily mean that we know they're TDEs. We just know they're in the survey, right? And that's where Fleet comes in. So what if we take all of those 10,000 TDEs and then run them through Fleet? And this is a preliminary experiment in which we did that. And we see if you see this blue curve, is just saying how many TDEs less than this redshift were recovered by Fleet. Where recovered means a probability of being a TDE greater than 50%. And it's around 30% of them for a redshift less than 0.5, which means of those 10,000 TDEs that were found in this theoretical LSST simulation, Fleet said, okay, I can find 3,000 of them. And this is better than I expected, just because this was trained on ZTF and ran on LSST using only GNR data points. So optimization to LSST will only make this better. But even at this point, we're already showing that this can be done and that it works to a reasonable degree. And I cannot leave without talking a little bit about Roman. I do spend half of my time working with Roman. If anyone has any questions, I'll be happy to talk to you about it. But we ran the same experiment with the Roman survey and find that it's probably going to find around 200 TDEs per year, which is way less than LSST. It's a smaller survey. But a key point here is that the difference between any TDE and a well-observed TDE is very small in Roman. So anything that Roman observes is probably going to be well-observed, whereas LSST is going to observe a lot of things with very few data points that are not going to be very useful. But it just comes to show that tools like this, like Fleet, like Refit, like Ghost, and Think, and all of these tools are going to be not only useful, but necessary in the era of big data. And with that, I will leave it open for questions.
Great, thanks, Sebastian. Let's take some questions.
Oh.
Let's also, we will come to, yes.
Thanks. Nice talk. So I was wondering for the higher redshift TDEs, how you model the rest frame ultraviolet. Are you assuming a black body from optical and sort of extending that out, or?
Yes.
Yeah.
So to generate the light curves, we use MOSFET, which is a code that just fits the light curves of superluminous supernovae, TDEs, and it assumes a black body. So I have that SED, and I can just say, okay, given any filter, give me the corresponding magnitude in that filter. So all of that is taken into account, the filter, the K correction, the redshift, all of that is built in. Yeah.
Yeah, thanks.
Great, who's next? I'll work my way across the room.
Thank you for the great talk. I was curious about at which point in the rise of the superluminous light curves does your algorithm tend to flag them as a high probability of being superluminous supernovae? Are you observing them before peak or kind of after peak, or how does that seem to pan out?
20 days. That is the, so if you look at a curve of how confident the algorithm is, before 20 days, it's terrible. It really can't do much. Once it gets to 20 days, it gives you a reasonable estimate. It's not great, but it's reasonable. And once you reach peak, past like 40, 50 days, then it reaches its maximum capabilities. But yeah, 20 days is the minimum. I need to like do something reasonable.
Great, thank you.
Okay, who's next? Said I would walk across the room, so here's Simon.
Okay.
Thank you. Very nice talk. This may be a naive question from a complete non-expert. So how do you distinguish like TDEs from just little flares of gas accretion that may also be there that we currently cannot observe, but LSST may do it?
You mean once you've classified it spectroscopically, or just like from the light curve?
From the light curve itself.
Yeah, it's hard. I can't. There's things you can do, but it involves getting more external data. Like for example, if you see that something looks like a TDE, it's in the center of a galaxy, it looks like a transient, but you see that it had previous variability in like WISE data, then you're like, okay, then that's probably an AGN and not a TDE. But at that point, you need to start involving data from other sources, and it complicates your pipeline, right? But yeah, just pure light curve, it's really hard.
Yeah, thank you.
Okay, I'm now halfway across the room, so I feel like I should dip into Zoom to take Dick Kessler's question. Are you there?
Do I do that, or I don't want to?
Come in, Dick. No? Okay. Well, then let's take another question in the room.
Great talk. I'm not a TDE person or a superluminous supernova person, but I was just generally curious with tools like these where you're getting, 50% of the true TDEs, for example. Are you worried that this type of method will bias your understanding of the population by preferentially selecting certain kinds?
Yes, that is a question I get every time, because it is a big question, not only for Fleet, but in the field. Just the nature of machine learning. We are inevitably going to find things that look like the things we already know exist, right? Because we have a training set that looks a certain way. So this is not perfect, but it is better than just using random selection cuts, because you are not imposing your own number on your search, right? But yes, at the end of the day, that is going to be a problem. Like for example, there's a big assumption here that TDEs happen in the centers of galaxies, because that's where the supermassive black hole is. But what if there's an intermediate mass black hole far off from the center of a galaxy causing a TDE? We would not find that. So yes, there are some things in which we are inevitably biased against. Yeah.
Okay, next question.
Great talk, Sebastian. My question is more related to the features that you use for making decisions for identifying TDEs. I know for superluminous supernovae you use the width as well as the rise time for, but can you say or comment about the main features which makes the decisions for identifying TDE?
Yeah. So we find that, well, being nuclear is very important, but one feature that we find helps us distinguish TDEs and it's very useful, that really doesn't help with superluminous supernovae, is the late time color. Because TDEs evolve at a very constant temperature, so if you see their evolution, let me see if, yeah. So in these plots, you can kind of see the difference between these colors and these colors, this and these, is very small. It doesn't really become redder with time like supernovae. So when you see something that looks like a TDE and then at the end of like 20, 40, 60 days later, it has the same color, that's a really good indication that you might be looking at a TDE.
So that might mean that it would take some time for the TDE to evolve, and then it, like late time colors, right? So it would take at least how many days for making a better decision, like?
Around 40 days.
Okay, thank you.
So for our next question, we'll go to Zoom, and I think Dick Kessler is back.
Oh, yeah.
There he is. Great, over to you.
Yes, all right, I missed last time. So with such small statistics, you're probably not probing the tails of the distributions very well. So have you tried simulating light curves where you push the envelope of color, duration, magnitude, and see how well Fleet performs in the tails of these distributions that we probably don't have in hand today?
One of the goals of Fleet is to use real data. So we have not done full-on tests with simulations, but we have done an exploration of how all of these parameters might or might not be biased from the real observational data. And we find that for anything that is not used as a feature, so anything like peak absolute magnitude, redshift, mass of the host galaxy, black hole mass, impact parameter, we find no real bias from Fleet. So the distribution of all of the TDEs and the ones recovered by Fleet seem to be very similar. There is some bias against parameters used as features, which makes sense because Fleet will give you a probability of something being a TDE based on these features. So obviously, there is an intrinsic correlation between how likely something is to be a TDE and the value of the host separation or its color. But in terms of physical features, it seems to be working pretty well.
Great. Bruno, did you have a last question? Okay, one last question from Bruno.
Yeah, I wanted to, can you go back to the slides where you show for LSST predictions? Yes. No, the previous one.
There?
Oh no, so then the following, there's a fraction.
There?
Yeah.
Yeah.
Can you explain me again that plot that you have?
Yes,
Fraction.
So what this is doing is, we have 10,000 TDEs that were found by LSST with enough data points to run by Fleet, right? It's the simulations, and we have the upper limits and the detections and everything. And we're saying, okay, how many of those, if we run them through Fleet, and Fleet is going to say, okay, given its Likert properties, we fit it, what's the rise time, what's the color, here's the probability of it being a TDE. Out of all of them, and this is cumulative, so anything lower than a redshift of 1, lower than a redshift of 0.5, if you look, you can just focus on the blue line. That is saying that anything with a probability of being a TDE greater than 50%, 30% of them were found. If I relax my assumptions and say, okay, I'm going to look at everything with a probability of being a TDE greater than 30%, which will also bring in a lot of junk that is not TDEs, then that fraction found goes up to 50%, which is our current prediction of Fleet, trained on ZTF to use on ZTF.
I guess my question is like, why is it flat? It's like if you're using a cumulative.
Yeah.
Are you taking into account the rate and the volume that you are probing at that redshift?
No, not in here. Like in here it is. So in the simulation, the volume it is taken into account. So that is why this looks like this. It's just a feature of commuting volume. But in here, it's just net numbers.
Okay.
Yeah.
And if I may, a very short one. You mentioned using OpSim.
Yeah.
But which observing strategy are you using?
1.7.
So
is there a newer one?
Is that YFastDiff, right?
Okay. Sorry?
So that's YFastDiff, but not DDF at all. Like
I can't hear you.
That's YFastDiff, right?
It's the entire. Well, it's the entire.
Okay, so you're not looking into the differences between a deep field and.
No, I'm not.
No.
It's just the whole thing. Yeah.
Great. Thanks for a great set of questions, everyone. Let's thank Sebastian again.